Hi there, welcome to my videos on elementary differential equations. This is video number 3 for chapter 8 and the topic is on Fourier series. We begin with a review of the formulas we derived in the previous video on Fourier series. These formulas are called Euler-Fourier formula for the function f of x with period 2L. And this is the expression of a Fourier series as a series of sine and cosine function with also period 2L. And the coefficients are these a's and b's. And the an can be computed by finding the integral over a period of f times the cosine function for n from 0 and 1 to 3. And for the b's, it's a similar here, but you multiply the function f with a sine function. And these are for n from 1 to 3. Because you see when n equals 0, sine of 0 is 0, so that's just 0. So that term is never there. And if the period shall be 2 pi, that is, if L equals pi, then the expression is a bit simpler. And the term pi over L equals 1, so it's shorter. And then you change all the L into pi, and with nx in the sine and the cosine function. Okay, so in this video, we will take our very first example to find the Fourier series. The function we will be using for finding Fourier series is a periodic function, and it's a piecewise constant, and meaning that it has a discontinuity. It's the following. The function is period with period 2 pi, and on the interval from negative pi to 0, it takes value negative 1, and from 0 to pi, it takes value 1, and it repeats itself, so it's periodic. And we can very quickly sketch the graph of this function. So over a period, this is x, and that's the f. And let's say this is pi, and this is negative pi. And we just need to sketch over here. Okay? And then we know that's 1, and that's negative 1. And we know on the, for x less than 0, here you just get, let me put a red color, so it's just negative 1 here, and then over here it's positive 1, and then it repeats. Okay. We see that we first observe that this is an odd function. We can easily see that on the graph, that the graph is symmetric about the origin. And in a more abstract setting, one can say that in a formula way, what is an odd function, that is a function f of negative x, will equal to the negative value of f of x. Okay, and this property comes in handy when we work out the integrals. Okay, now we use the Euler-Fourier formula with L equals pi. That's a bit simpler expression. Let's first compute a0, which the formula says 1 over pi of the integral of fx times 1 dx. And this is negative 1 on this interval, and positive 1 on this interval. So on this interval, the integral will be negative pi, and on this it will be pi, and they cancel each other, and that's 0. And you can also be less specific and use the abstract property that fx is an odd function. It satisfies this expression. Therefore, integrating over this period, which is symmetric about the origin here, we'll get 0. Okay, so next we compute the an's for n bigger than 1. We use the formula, and this will be the formula. And now we use the fact that f is piecewisely defined, and therefore we break it into two intervals. And we integrate from negative pi to 0, where this f is -1, so we get just negative sign. And then the second interval is from 0 to pi, where f is 1, so we just have cosine. And we can work out the integral of a cosine. So for this negative cosine, we have 1 over n negative of sine nx. And this is evaluated from negative pi to 0. And similar for the cosine here is 1 over sine n pi x from 0 to pi. But we see that both the upper and lower limit of this is 0, because sine of 0 is 0, sine of n pi is 0. And the same happens here, sine of n pi is 0, sine of 0 is 0. So in the end, we just get 0 for all the an's. Actually, there is a much quicker way of computing this integral by observing the following. So we see that fx is an odd function. And then we also know that the cosine is an even function. And then in the end, we are making a product of these two functions to be integrated. So the product of an odd and an even function is in the end an odd function. And then we integrate over a period symmetric about the origin, and such an integral of an odd function is 0. So you actually don't need to carry out any of these computations. You just need to observe that fx is odd. Okay, so that can be a trick we keep in our pocket for later use. Now we compute the coefficients b's. So this will be the integral of f times sine nx. Again, we break the integral on two intervals from negative pi to 0, f is -1, and from 0 to pi, f is 1. So we need to work out these two integrals. Okay, so we know how to integrate a sine. Okay, as integrate of sine is a negative cosine, and then we have a factor 1 over n, and then this negative comes from this negative sign here, and this is taking the endpoints from negative pi to 0. And let's look at this integral. So when x is 0, you have cosine 0, and then when x is negative pi, you have cosine negative n pi. Okay, and this negative sign cancels this negative sign. So cosine of 0 is just 1, and since cosine is an even function, so negative n pi of cosine is just cosine of n pi. So the first term ends here. And the second term integral of sine is negative cosine, and that's evaluated from x equals 0 to pi. And let's put it in x, put the negative sign over here, and x equal pi, I get cosine n pi, and then x equals 0 is cosine 0. And then we can use the fact that this is just 1, and we can distribute the negative sign in here and get a plus sign, and this will be positive 1. This is negative cosine n pi. Okay. And we do observe that these two terms are actually the same. Is it a coincidence here, or is there something else? Okay, let's first add them up, and by just multiplying a term by 2, because these two are the same. And that will be our Bn. It's now written in such a way that 2 over n pi, that's a constant term, and then we have this term cosine of these numbers that are just n pi, multiples of pi. Okay, so let's make a remark on the fact that we observe that this term is the same as that term. So this actually comes from the fact that our function f here is an odd function. So okay, so let's remember f is an odd function, and we also know that sine is an odd function. Then the product f times sine, you multiply two odd functions and you get an even function. And if it's an even function and you integrate symmetrically around the origin, and you know that the integral on the negative half and the positive half, they are exactly the same. So you just need to carry out one integral and multiply by 2. Okay, so for this case here, you can just say drop this one and only take that and then multiply it by 2. Okay, and you would get the same answer. Okay, so for this expression, so this is our Bm. Now we wish to express it in a better way. We would evaluate the cosine function at n pi and see what we get. Okay, let's look at a couple of the values. So when n equals 1, cosine pi we know is -1. When n equals 2, cosine 2 pi is just cosine 0, which is 1. And after that, we can use the periodic property that cosine 3 pi is just cosine pi, because you can remove a 2 pi, which is -1, and so on and so forth. So we see that for odd n, we'll get -1, and for even n, we'll get 1. Therefore, we can write as following. Cosine n pi is -1 to the power n. Okay, let's plug this back into the Bn. It's now 2 over n pi times 1 minus cosine n pi. We write it as -1 to the power n. So this term here will depend on n being even or odd. If n is odd, this term is -1, and this gives us 2. We'll get 4 over n pi. And if n is even, then this term is 1, and we get 1 minus 1, and Bn will be 0. Okay, so we see that all these Bn's are 0 for even, odd, and they're only non-zero for odd ones. Okay, we can write out the first few of them. Let's look at B1. Now that will be 4 over pi when n is 1. And then when n is 3, I'll have 4 over 3 pi. And then when n is 5, I'll have 4 over 5 pi. And then when n is 7, I will have 4 over 7 pi. So on and so forth. Okay, now we have found all the Fourier coefficients. We can now write out the Fourier series. Since all the an's are 0, then we'll only have sine functions. There'll be no cosine functions. And since we also know that all the Bn's are 0 for n even, therefore we'll have only the odd terms. So we have the summation for n odd and Bn times the sine function. Okay, we can put in the expression of Bn, and we see that 4 over pi is a fraction that does not depend on the index n. We can take it out, and then we have this factor out, and the summation summing over all odd n, 1 over n of the sine function. Here we will write out the first few terms just to take a look at what they are. We have 4 over pi outside, and we collect these terms for a few n numbers. Let's say the first one is n is 1. We get sine x, and the second one is n is 3. Then 1 over 3 sine 3x, and the next is n is 5. 1 over 5 sine 5x. And for n is 7, we'll get 1 over 7 sine 7x, and plus, so on and so forth. And let me mention one more thing. So instead of writing the summation sign over n and specify then n is odd, we can do the following. We can define the index n and let it just run naturally from 1 to infinity, and change this into 2n minus 1, and then this will go through all the odd numbers. when n is 1, this will be 1. When n is 2, that's 4 minus 1, that's 3. When n is 3, and this will be 5, so on and so forth. So we can write it like that. Okay, now we introduced the concept called the partial sum of a series. The partial sum meaning we don't take the whole series, we take the sum of the first few terms. Depending on how many terms you take, we can denote the partial sum to be yn, where this number n here will be the number of terms, the first n terms in the Fourier series that we take. Take our example, we have written out the first few terms like that, then we can have the partial sum. So what will be the y1? Well, they'll be taking only one term, then that's the 1. And then y2 will be taking 2 terms, this one and that one, and we put it here. Okay? And then for y3, we'll take 3 terms, 1, 2, and 3. Then we get that. And so on and so forth. So you can define as many terms as you like. So an interesting question to ask is the following. If we take a few terms, how does that partial sum approximate the function that we wish to write into Fourier series? And if we take more terms, do we get a better approximation? So this question eventually will lead to the concept of convergence of the series. Then we see in the partial sum, if we let n go to infinity, then we'll be summing up infinite terms, and this will eventually give us the whole Fourier series. Okay, so we now present some plots of the partial sum against the function f to see how it approximates. This is for y1. We know y1 is just a sine function, and our function is -1, jump at 0 to 1. It's piecewise constant, and we see that if you approximate it with just a sine function, then this graph here is approximating it as best as it can. It captures the main feature that it goes down to -0 and it crosses 0 back to the positive part. This is the partial sum of y2, that is, we have 2 terms. We have the sine x and the sine 3x. And you see that this apparently is a somewhat better approximation than the y1, in the sense that here it doesn't overshoot as much and it tries to oscillate around it to approximate the value -1, and the same thing happens here. And the way it's overshooting or undershooting here is not as big as the y1 term. Okay. This is the plot for the partial sum y3, where we have 3 terms, sine x, sine 3x, and sine 5x. And we see that it's even a bit better. It tried to approximate this function here by going around it more times, and the same here because it's symmetric. And the overshoot here is even smaller. So it looks like taking more terms, then the partial sum seems to be a better approximation of the function f. Okay, so here is the last graph of the video where I plot all of them together. So let me explain. So the black one here is the exact function, which has a jump. And the red one here is y1, that's the partial sum with just 1 term. And then the blue one is y2, which contains sine x and sine 3x. Okay, and then the green one is the y3, which contains, in addition, also sine 5x. Okay, so you see as the partial sum terms gets higher and higher, this is getting steeper and steeper because it eventually would like to be a good approximation of a discontinuous jump right here. Okay, so this is our first video on example of Fourier series, and we go through it with some details, and next time we will look at more examples. Okay, so, and there will be more details and more ways of performing the integrals. Okay, so I hope you enjoyed this video, and I'll see you next time.